6.2. So radical expressions and functions and rational exponents. So we'll start with the square root because that's the radical that most of us are most familiar with. And then we can generalize to higher index radicals. So we'll start with just your basic definition. We say that C is a square root of A if C squared is equal to A. So this definition is what we call a recursive definition, which just means that it doesn't actually tell us what to do with A to find the square root. It tells us that if you do something with the answer and you get A, then that's a square root. So it's kind of defined backwards. For example, we say that 6 is a square root of 36 because 6 squared is equal to 36. It is also true that negative 6 is a square root of 36. Because when I square negative 6, I also get 36. So negative 6 squared is equal to 36. So we know that squaring a number and squaring its opposite will always result in the same thing, the same positive number. So we can generalize and say every non-negative real number has 2 square roots. So there's the negative square root, and then what we call the principal square root, which is just the positive one. So for 36, we say that 6 is the principal square root of 36, and negative 6 is the negative square root of 36. So it's a little bit troubling that we have 2 square roots because we would like to be able to talk about the square root operation in terms of a function. So we like to have just one output. Whereas here, if I say, what's the square root of 36, there's 2 possible answers to that, which means that all the stuff that we know about functions can't be applied to that. So in order to get around that, we define the radical symbol, so the square root of A, to be the principal square root only. So the principal square root of A. So it's always a non-negative number. And that allows us to write a function f of x equals the square root of x. And we get a little bit lazy when we write that radical symbol. We usually just say square root. We don't say principal square root every time. But it's assumed to be, as long as we use the radical symbol itself, it's assumed to be a non-negative number, so the output of it. And so that allows us to define the square root function and have it actually be a function. So when we input 36, the only output here would be 6. What's the domain of that function? Yes, domain. We've done this before.
Would it be all reals?
So can you take the square root of a negative?
Oh no, it would be all positive numbers.
So it's all non-negative numbers, which is really close to all positive numbers. It just includes 0 as well. And then because we defined that symbol to represent only the principal square root, that means that the output is also non-negative. So the range is also 0 to infinity. So let's take a couple square roots. Let's look at the square root of x squared plus 4x plus 9. Not 9, 4. So just like when we worked with fractions, if there's addition or subtraction under the square root or under the radical, we have to group it all as a single number. We cannot take the square root of individual terms. So the only way to simplify this is if we can factor that polynomial, which we can. It factors into x plus 2 times x plus 2, also known as x plus 2 squared. So what do you have to square to get x plus 2?
X plus 2.
Oh, sorry, I said that wrong. What do you have to square to get x plus 2 squared? Yes, x plus 2. So this is equal to x plus 2, sort of. So this brings up a bit of a question, because suppose that x was negative 10. So plug negative 10 in there and see what you get. So if I have negative 10 right here, is that a true statement? It's not, is it? Because if you do negative 10 plus 2, you get negative 8. But negative 8 squared is positive 64. And what's the square root of positive 64?
8.
It's just 8, right? Because we define that symbol to represent the principal square root, and that is not a true statement. So we need one little adjustment. What could I do to negative 8 to make it positive? I mean, I could multiply it by negative 1, but without involving any other numbers, what operation makes every number positive? So, but I don't want to involve any other numbers. So I don't want to multiply it by anything.
Addition.
I'd still have to add it to something. Like I'd have to have another number. Yeah, the absolute value, right? When you take the absolute value of a positive, you get a positive, and the absolute value of a negative also gives you a positive. So if I said this, Now would that be true?
Yeah.
Now we'd get a true statement. So in reality, the square root of x squared is not equal to just x like we would like for it to be. It's actually equal to the absolute value of x. And that accounts for the possibility that x is a negative number or a positive number. However, we will assume that all variables represent non-negative numbers. So that the square root of x squared is actually equal to x. So we make this assumption only so that we can get comfortable working with radicals without having to worry about the absolute value every single time we simplify a radical expression. Once we're comfortable with radicals, then we'll be like, oh yeah, not every number is positive, or not every variable represents a positive, so we have to include the absolute value. But it's a lot easier to work without the absolute value as you first get comfortable with it, and then we'll go back to reality eventually. But for now, it just allows us to manipulate the radicals without having to also manipulate absolute values. So we will make that assumption when simplifying radical expressions for the foreseeable future. So we are allowed to say this. Okay, so that's our square root. Next we want to talk about the cube root. So I'm just going to actually just copy this guy. I don't need that. Okay, I'll give you guys time to write, but I'm just going to like erase, make sure I get everything. So we say that C is a cube root now. Of A if C to the third is equal to A. So the square root corresponds to an exponent of 2, but the square root won't undo an exponent of 3 or 4 or 5 or 6 or 7. So every exponent has a corresponding radical, which undoes it. It's the inverse operation. So inverse operations we use for things like solving equations, like multiplication and division are inverses of each other because they undo each other. If we want to undo, if we have like 5x, we divide by 5, right, to undo that multiplication. Addition and subtraction are also inverse operations. And so radicals are inverse operations of exponents. However, we don't have just one radical that can undo every exponent. So every exponent has a corresponding root which undoes it. So an exponent of 3, the inverse operation is the cube root. So we can say, for example, that like 2 is a cube root of 8 because 2 to the third is equal to 8. And then we saw with square roots that every square root has 2, or every positive number has 2 square roots. So is it also true that negative 2 is a cube root of 8?
No.
Yeah, it'd be negative 8, right? Because if you raise a negative number to an odd power, you get a negative number out. So remember when we were talking about domains, we said that with the square root or even roots, there's a restriction on the radicand. It has to be greater than or equal to 0. That restriction doesn't exist with odd roots because you can take the cube root of a negative number. The cube root of -8 would be -2 because raising -2 to the third power does actually give us a negative number. So every non-negative real number, and we don't even have to have non-negative anymore, every single real number has one cube root. The cube root of a positive number is positive. And the cube root of a negative number is negative. And symbolically, we use a radical symbol to represent the cube root as well, but we actually have to write our index. So that 3, it's not like 3 times the square root of a, it's just the cube root of a. And that 3 is kind of in just like that little nook in the radical symbol to tell us which exponent that radical undoes. So is the cube root of
So was the stuff that was written up there, was that like another thing that we should write down? Or
You already wrote it down. Yeah, when we talked about the square root. So if f of x is equal to the cube root of of x, what's the domain of that function? All real numbers, because I can take the cube root of negatives, positives, and 0. So what's the range? Do you guys remember from when we did basic functions? Remember the graph of the cube root? It's the range of that function.
It would be negative and all reals.
Yeah, it's all real numbers again, right? Because the cube root of a negative is a negative, so you can get a negative output. The cube root of 0 is 0. And then the cube root of a positive is a positive, so you can get a positive output. So we can get any output as well. So let's do just a couple examples. We already saw that the cube root of 8 was 2. What's the cube root of 2 to the third? So 2 to the third is 8, and then the cube root of that is 2. Good. What about the cube root of negative 2 to the third? It's negative 2, right? Which is a little different than when we were working with the square root, right? Because we had that absolute value, because our output was always positive. So here, whether x is positive or not, the cube root of x to the third is x. There's no absolute value with odd roots because you can input a negative and you can get a negative output. So let's generalize all of this. So we looked at the square root and we looked at the cube root, and those are examples of even roots and odd roots. And it turns out that all even roots basically behave like the square root, and all odd roots basically behave like the cube root. So if we come back here, we can rewrite all of this and say that C is an nth root of A if C to the n is equal to A. So where n is just any number, we're saying the nth root undoes an exponent of n. So for example, let's see, how about the sixth root of 64 is what?
92.
I feel like that's the only one I can really do because the rest nobody knows off the top of their head. And they're huge numbers. I mean, the numbers get pretty big. But so the sixth root of 64 is 2 because 2 to the sixth is equal to 64. And again, every positive number has 2 sixth roots or eighth roots or 10th roots, just like with the square root. So every non-negative real number has 2 nth roots. If n is even. And we define the nth root of A to be the principal nth root of A. So again, we use that radical symbol to represent just the positive nth root, if n is even, so that we can have a function and we say f of x is the nth root of x, where n is even. And then the domain and range are just the same as what they were for the square root. So technically speaking, the square root would be written like that. It has index 2. We call n the index of the radical. Because the square root is the most common one that we use, we don't write the little 2 for square roots. So if there's no index written, then we assume that it's an index of 2. I mean, you could write the index if you wanted to. It's just convention not to. So it's a little bit of an adjustment because we're pretty used to every time we see the radical thinking of the square root. But you want to remember that that's only if the index is 2. So as soon as we change the index, that radical isn't a square root anymore. It's a 4th root or a 5th root or a 6th root or a 7th root. So all of this is true for even roots. And then we can generalize odd roots as well. So just like we said before, C is an nth root of A if C to the N equals A. So what's the, oh, I don't know, let's do 7. What's the 7th root of -1? What would you raise to the 7th power to get -1?
1.
So 1 to the 7th would be
Negative.
1, right? 1 to the 7th? So 1 times 1 times 1 times 1 times 1 times 1 times 1 would give you 1, right? So it would be -1, right? Because -1 to the 7th power is equal to -1. So every real number has one nth root. If n is odd. So just like the cube root, any odd index radical we can apply to negative numbers and also to positive numbers, and we get a single output. So we define the nth root of A to be the nth root of A. And if we write a function, f of x equals the nth root of x, where n is odd this time, then the domain and range are just the same as what they were with the cube root. All real numbers for both. Because we can, if n is odd, we can take the cube root of a negative, we can take the cube root of a positive, or sorry, we can take the nth root of a negative, we can take the nth root of a positive, we can take the nth root of 0. Let's find some domains. Let's find the domain. Of each function. We'll do f of x equals the square root of 9 minus x. So how do I find the domain of a square root function? What do we know about square roots? So what we take this square root of has to be positive, right? The radicand has to be greater than or equal to 0. So whatever it is I'm taking the square root of has to be greater than or equal to 0. And that that inequality symbol always faces the same way. So it's always greater than or equal to 0. The only time you'll have it facing the other way is if you have to switch it as a result of solving that inequality. When you write the inequality, it's always the radicand is greater than or equal to 0. And then to solve that, we would subtract 9 from both sides. And then I have to divide both sides by -1, which would switch the direction of my inequality symbol. So people sometimes ask, like, how do you know which direction it faces? And it when you set it up, it always faces the same way. The radicand is always greater than or equal to 0. It's just in the process of solving the inequality that sometimes you have to switch the direction of the inequality. So our domain would be negative infinity to 9, including 9. How about this one? How do I find the domain of that? What about it? Well, we're not simplifying. We're finding the domain. So we're trying to find the set of numbers that I can plug in for x, for which this would be defined. I'm pretty sure, haven't we found the domain of square root functions before? So how do we do it? Mm-hmm. The radicand has to be greater than or equal to 0.
Wouldn't that just be all those?
Yeah, very good. So x squared is always greater than or equal to 0, right? That's always true because if I square a positive, I get a number greater than or equal to 0. If I square a negative, I get a number greater than or equal to 0. And if I square 0, I get 0. So this is always true. So my domain is all real numbers. Let's do the fifth root of 3x minus 7. What about this one?
All real numbers.
It is all real numbers. Good.
Is it okay if we use the IR instead of writing negative infinity?
Yes, but it is not IR. It's an R that happens to have 2 lines for the up and down. It's just a different font. Okay, so let's talk the relationship between radicals and exponents, because that's what's really useful, is when we can go back and forth between the two. So again, let's look at the square root first. Suppose that I had x squared and I raised that to some exponent which undid it, so just gave me x. What would a have to be? So that would be true if we were multiplying, right? So like, because if we were adding these exponents, then -2, well, that would give us an exponent of 0. But remember that when we raise an exponential expression to another exponent, we multiply exponents. So we have x, this is x to the 2a. What is the exponent on x?
1.
Yeah, it's 1 factor of x, right? So that means that whatever I multiply 2 by to get 1 is what a would have to be, right? So what's a?
X squared.
So it's just a number. It's the number you multiply 2 by to get 1.
Like, should multiply
You can.
Oh, 1/2.
1/2, yes. Right? 2 times 1/2 is equal to 1. So that means that the square root of x is the same as raising x to the 1/2 power. Because the square root of x undoes an exponent of 2, right? And then we just saw that an exponent of 1/2 also undoes an exponent of 2. So they are the same thing. In general, the nth root of a to the m is equal to a to the m over n. Because the nth root is the same as raising to the 1 over n power, and 1 over n times m is just m over n. You should write this really, really big and put lots of circles and stars around it. It will answer 95% of your questions tonight on your homework. Like, it's like the thing. We use this a lot in calculus because a lot of our derivative rules tell us what to do with exponential expressions, but they don't tell us what to do with radical expressions. So in calculus, we basically write everything as an exponential expression. So if we can write something with an exponent instead of some other symbol, we do it. However, when it comes to going back and forth between exponential form and radical form, there's not like one that's more simple than the other or more correct than the other. It just depends on what situation you're in. Sometimes it's more convenient to use radical form, and sometimes it's more convenient to use exponential form. So we'll do a couple here to see the different ways we can use each. But for our purposes, since we're not doing this within a bigger problem, and so it's not obvious which form is going to be the most convenient, you just have to read the instructions really carefully. So the instructions will tell you if you should give your answer as an exponential expression or as a radical expression. And there's not like, it's not going to be like, there's not like a rule as to how all the answers should be. It's just whatever the instructions tell you to. So let's do a couple. One of the places where it is convenient to use rational exponents is if I have something like the square root of x times like the cube root of x. We're going to simplify and write the answer without rational or negative exponents. Using radicals as necessary. So often, even if we want our answer to be in radical form, rational exponents will help us to get to a simplified answer. So if I want to multiply these two, I can't just multiply a square root by a cube root because they have a different index. If I put both under the square root, then I've changed that I was taking the cube root of one of them and vice versa. But I can write them both with rational exponents. So the square root of x is the same as x to what power? 1/2. Good. And the cube root of x is the same as x to... So what's the index? 3. So the 1/3 power. And we have rules for exponents, right? We know how to multiply exponential expressions that have the same base. We just add the exponents. So this is x to the 1/2 plus 1/3, which you can put in your calculator and get x to the 5/6. But we want our final answer to not have rational exponents, so we want it to be in radical form. So we're going to go back to a radical. What should my index be here?
6.
Good. And then my exponent will be 5. So the 6th root of x to the 5th. So we were able to simplify that product into a single radical expression by kind of going through the exponential form. So it can be very useful to write radicals in exponential form to allow us to do some operations that we can't do in radical form. Sometimes it's convenient to go the other way. For instance, if I have 9 to the negative 1/2, well, we don't want negative exponents. So how could I rewrite this with positive exponents? I like when you guys mouth the answers instead of actually saying them. How would I write it with a positive exponent? So you would do the reciprocal of 9 to the positive 1/2. Good. Be careful with what you're taking the reciprocal of. It seems like as soon as the exponents are fractions, people want to take the reciprocal of the exponent instead of the base. But remember, just like we did when we had whole number exponents, to change the sign on the exponent, we take the reciprocal of the base, and then the exponent itself stays the same other than the sign. So we go from a negative 1/2 to a 1/2 exponent, and then the reciprocal is of the base. But what's 9 to the 1/2 the same as? So did you get that by putting 9 to the 1/2 in your calculator? Okay, so without your calculator, what is 9 to the 1/2 the same as?
Oh.
Remember when I said that that will answer 95% of your questions?
2 square root of 9.
Yep. It is the same as the square root of 9. And we don't have to write the index of 2 just because it's the square root, but if you want to, you can. It doesn't hurt. And then we know that the square root of 9 is 3, and so this is equal to 1/3. We need to be able to do that without a calculator, because if that was an x instead of a 9, then your calculator is not going to do anything for you, right? Or really any other number that's not a perfect square. Let's see what else. I mean, that's really it. Like, this stuff truly, like, isn't, like, there's not a whole bunch of variation in how you do these problems. Again, like, this will answer basically all of the questions. Where your homework is really just going back and forth between exponential form and radical form. So if you can remember the index, well, you don't even have to remember it. You can just put that down in front of you while you do your homework, right? The index is the denominator of the exponent, and then the exponent is the numerator of the exponent. So tonight you have my math lab and then a worksheet.